Hi everybody. I just want to do a little preface to this video. This is all complete right now at this point that I'm filming this part, and I'm going to put this at the very beginning of the video. This is probably going to be a very heavily edited video, and the reason being was because of the adventure that it turned out to be. It really wasn't an adventure as far as troubleshooting or repairing went, but it was an adventure in finding things out as I went along. When this first was brought to me, by a person who's a collector of this, there was almost no information available. We could not find anything on this. No schematics, no block diagrams, no instructions, no user manual, no owner manual, nothing. Some of the other items built by this company were were out there, but nothing for the AM5 and the DA9 and the DA7, which is the other antenna you're going to see in this video. As I continued working on this, as it was on the bench, we were in the process of trying to reverse engineer a few things. Little by little, the owner of this equipment started finding, making contacts with people he knew, and he actually was able to acquire a good schematic, a block diagram, and even a magazine article, a clipping from a magazine article describing all of this. When we put all that together, it really changed the whole face of this video and really changed what we were able to show you in this. So it turned out to be a really interesting video. I also have a piece of sad news. Our little physicist, our physics professor, Cookie, our cat, unfortunately passed away over the weekend. And you can imagine my wife and kids and even myself how sad we are that she's not with us anymore. It was a lot of fun trying to figure out how she knocked that cup over. If you go back and watch my video on the 2500, the Marantz 2500, you'll get an idea of what I'm talking about. But we had her for 13 years, and early on in life she developed a heart murmur and struggled with that, but was a really healthy cat pretty much her whole life. And it was very, very sudden. She was playing and having fun in the morning, and that evening she was gone that quick. So anyway, we wish Cookie the best, and I wish you all the best. I hope you enjoy this video because I really enjoyed making it. It was quite a journey. It was a lot of fun. All right, here we go. Oh boy, how do I get myself into these messes? So here we have in front of us three very rare pieces of equipment made by a company called McKay Dymek, or just Dymek. It was made a company that was I believe, out of California. And believe it or not, all of this is just AM broadcast tuning only. It's a couple of very rare pieces of equipment. I don't think they come up very often, and when they do, I think they're pretty pricey. I've never had the chance to work with them, and to make matters worse, there are no schematics, no service manuals, nothing that I could find available for these at all. So this is going to be quite a challenge to figure out. The person who brought them to me as a complete set. He is a collector of a lot of this kind of stuff, so he brought all the pieces in together. Essentially, the way this normally used to work was, this is the model AM5 AM receiver. There is no amplifier in them. It is a tuner only, and it is an AM broadcast band tuner only. Just a very good one. And then it was designed it can stand alone, or it could work in conjunction with one of these two. There's actually a third one called the DA5, and these are like active antennas. So you have the model DA7, the DA9, and then there was the DA5. Now, there were some slight differences. If you notice, the DA7 has a medium and long range switch on it. This one does not. The circuitry is a little bit different, but they all do the same thing. They're basically amplified active antennas, and they kind of go in conjunction. They can be connected to any AM tuner, but they also work very well with the AM5 tuner. So these are supposed to be really amazing tuners. And I'm repeating what I've heard, not what I've experienced. I have never heard one of these, seen one of these, tried one of these. I've seen pictures of them, and that's about it. So here it is on my bench. No schematics, no alignment manuals, no nothing. And that's why I started out the video by saying, I don't know how I get myself in these messes. But anyhow, I think this is going to be a lot of fun. This will be a fun project. And I'm sure any of you who are really into AM DXing will be interested in this video and in these three products. So let's start and take a look at what we've got here. I'm going to go to these antennas last. We're going to start with the tuner and see, number one, if it works, and number two, if it needs anything. And then we'll go from there. Okay, looking at the front of this thing, there's not much going on. You have a little panel meter, you have your actual dial scale, a tuning knob, on-off switch, distance and local, narrow band and wide band for your filter. That's it. That's all there is. And turning it around actually is, to me, is a little bit more interesting. So let's look at that. If we look at the back, it has some outlets. It is switchable between 115 and 240 mains. So you can run it on European or American power. It has two antenna inputs. Notice 50 ohm terminated antenna. And these two little holes are actually antenna trimmers. So it actually has an antenna trimmer for your antenna. It has an audio output, and then it looks like there's an option. I don't know if that's for an output or an input. I don't have the instructions for this, so I'm not sure. And then, of course, an audio level output. And remember, this is just a mono output that goes to an amplifier. So you could probably plug this into just about any amplifier you have. Other than that, there it is. Very simple. So I took the two screws out. And we're going to open this up. Of course, I always like to check things out before I plug them in, because you never know if something's been loosened or shorted or something's wrong. And I hate to damage anything further, especially something this rare. So we open it up. And this is all solid aluminum, or aluminium, as I hit the camera with it. And if we take a look down inside here, this is a pretty well-built little tuner. So take a look at that. So we see a 3-gang tuner in the front end. And let me look at it. Kind of looks like they split this up into modules. So you have your switch up here, and there's two little Murata ceramic filters, and I'm assuming that's your wide and narrow IF filtering. They're putting up here right next to the switches. This is the power supply. This looks like your RF and IF all in one, and then this here must be your audio and detection, or I'm not sure. I'll have to really look at it. But the thing I do notice is all these really good quality film capacitors. The one scary thing is it uses these funny domed transistors, and these are kind of, I don't know, I've had some issues with these on other gear in the past. I had a whole box full of brand new ones that were never used from Lafayette Radio Electronics when they went out of business a long time ago. And you'd put them in, and sometimes they'd work and sometimes they wouldn't. They were just kind of funny. So maybe they'll be good, maybe they won't. I don't even know if those are transistors. I think they might be. Or no, maybe they're, no, they look like FETs. So those are FETs. They're in the same case, but they're not bipolar transistors by the looks of it. So I don't know how many stages of RF amplification this thing has. I'm going to have to really study this to see what's going on. Rubicon capacitors, which I would imagine these caps are all good, but other than that, I bet you this thing's spot on. I don't see anything in here that could go out of alignment unless somebody actually moved it, and none of this looks like it's ever been touched. So I bet you if we plug this thing in, it'll work. Another thing I noticed, a really nice feature, they put the RF shielding on the transformer, and they placed the transformer and all the voltage away from the antenna, although I do see the antenna wire running right against the transformer, but it's so heavily shielded coax that I really doubt that any of that's going to cause any problem at all. I don't think we'll have any coupling of noise. So yeah, this all looks very interesting. I think we should try to plug it in and see if it works. I'll connect it to my vertical antenna outside and see if we can pick anything up. Okay, I just have this little Radio Shack amplifier set up, and I'm going to just kind of move it back here so the microphone can pick it up a little bit better. Of course, we don't care about fidelity right now. All we want to see is if this thing tunes. And I'll hold the speaker back here and see what it does, and we'll turn it on. Okay, here we go.
By for-profit businesses, corporations. But it's worth the question to ask your employer. This is why you should definitely...
Okay, even on the weekends the phone rings, you never know. So, okay, let's continue.
...developed have practical application in commerce. Companies that are...
That's 877.
In this product for years, including its previous version.
Gee, thanks.
But it went
technologies and other companies that are making profits.
Your business, your husband's business is on.
Indiana checks into today's matchup with a 14-14 overall record.
If it's qualified money, you're going to have to take required minimum distributions beginning at 8.
Apply today.
The fun begins Saturday at noon.
We're going to do it on the other side here. I want it.
It's space that they don't have a lot of left, and they just...
So I guess you get the point. This is the middle of the day. It's not nighttime. I'm not DXing. And you could see, you know, this is a ham radio antenna that I'm connected to. I mean, yes, it'll go in the AM band, but it's actually not even really very good for 160 meter band, let alone AM broadcast. So even with that, and I didn't mess with the antenna trimming coil in the back or anything, you see what this thing does. So, and you can see how wide all of the scale is spread apart, and to allow it to have, you know, more adjustment, because of course this doesn't have a band spread or fine tuning. It just has the main tuning knob. I'm on wide bandwidth right now, but what is there to do with this other than change the caps? I guess what I'll do is we'll try to find a little bit more about how this thing works, because I'm sure not going to mess with it. I may hook up some test equipment just to see what kind of performance we can get out of it, and maybe we'll do some SINAD measurements with our software, and then we'll move on to the antenna, I guess. Alright, so this isn't really a fair test for this particular receiver, because we're kind of applying some of the rules that you would use for like a communications receiver, like a CB radio or a ham radio or something. But what we're doing is we're just doing the basic 12 dB SINAD test. And essentially what we're doing is we're trying to find the point in signal strength at which you get down to about 12 dB of SINAD. Anything below 12 dB SINAD is considered not really good to even listen for voice. Now again, this is not a very good test for AM broadcast, because a lot of times you're listening to music, but if you're listening to talk radio, this is actually a pretty valid test. So as you can see right now, I'm above 12 dB cyanide, and I could probably go down a little bit further, so let's try. I can go a little bit more. And there we go. We're right now bouncing between 11, 12. We're a little bit low. Let me go up a little bit more. And right there's pretty much a fair place. So you can see there's a lot of static on our audio. That's what we're looking at, is the audio. And down here is your dB cyanide, which is right now right around your 12 dB. And if we look, we're at about 91 dBm. Now this is a really easy radio to test because it has a 50 ohm terminated antenna jack, so we can just take a direct 50 ohm cable, go straight out of our signal generator and straight into there. No impedance matching, nothing. So you can see with about negative 91 dBm. Now understand, communications radios such as a good quality CB radio, Citizens Band, or a shortwave communications radio, they can get down in that 120 to 122 negative dB, negative 120 to negative 122 dBm range. But for a communications or a broadcast band radio, this is actually pretty good. Remember, the design of this is different. One of the things that these radios here are supposed to be noted for is their fidelity. In other words, they have a very wide frequency response for an AM radio, and the trade-off on that is a little bit decreased sensitivity. So an AM radio is typically not going to be as sensitive as a communications receiver, such as an ICOM or Yaesu shortwave radio operating in that band. So again, we're only using 30% modulation. That's another thing. When you do this test, you do it at 30% modulation, but if you're checking for audio, your modulation can be much higher than that. And of course, if we increase the modulation, your cyanide's going to go way up, which is good, and so forth. So I'll show you, if we go up to just 50%, you can see what an improvement it makes. Let me see, I get everything in there? Oh yeah, we got it all in there. You can see that the cyanide goes up to almost 16, 17 per dB. And if we go up closer to maybe 70%, you can see the amplitude of the signal gets much higher. The static versus that goes lower, and our cyanide gets much better. And we can kind of adjust our tuning a little bit, and now I'm even peaking into 20 dB cyanide. So kind of gives you an idea of how this thing performs, which actually, as AM tuners goes, is pretty good. So, and I bet you we may be able to adjust this a little bit if we had the instructions and get a little closer, but this is kind of where we're at right now as the radio tuner came in. Okay, well, I'm feeding a signal of negative 50 dBm, and on the receiver, the signal indicator is indicating 9 S units, an S9, and you can see I've set this up so that my amplitude is about 1.2 volts peak to peak, and we can see that we have a very respectable THD, and we're at 1 kilohertz. And what we're going to do is, I'm on the wide bandwidth, so the wide filter, and we're going to just see how the frequency tracks on this. So we're going to go to a low frequency and kind of see where it starts to taper off, and then go to a high frequency and see where it tapers off. So let's do that. There's 900 hertz, 8, 7, 6, 5, 4, 3, 2, 100 hertz. And it's still holding amplitude. And 90, 80, 70, 60, 50. There's 50 hertz, and we're still getting a very respectable distortion. 40 hertz, 30 hertz, 20 hertz. Wow. There's 20 hertz. That's about as low as we can hear, and you can see this receiver is picking it up perfectly. That's pretty amazing for a tuner. Now let's go up in frequency. Okay. There's 1 kilohertz. Let's see how flat it stays. 2, 3. It's actually getting higher in amplitude. So right around 2 kilohertz, the amplitude, or actually 3 kilohertz, the amplitude starts to go up. Let's keep going. 4, 5, 6, 7, 8. Right around 8 kilohertz, it's back down to normal. 9, 10. So 10 kilohertz, there's a massive drop off. 9 kilohertz is still pretty good amplitude. You could see just a tiny little drop. So this is a very bass heavy receiver is what that's showing us, which is perfect for AM broadcast. And actually, clear up to about 99.5 kilohertz is pretty respectable, and then it'll start dropping off rapidly after that. Oh, by the way, if you notice, I put it at a really odd frequency, 685 kilohertz. And the reason that I did that is that's a really nice dead zone on the dial. This is a pretty hot receiver, and it'll pick up noise, you know, even without having an antenna connected. So that's why I chose that. Okay, we have some schematics here now, and now that we've done like a baseline test of the performance of this thing, we're going to go through and see if we can't figure out how to align this. Now this is going to be a little bit challenging because we don't have any alignment instructions, but what we do have is some schematics here. And the first thing we need to do is we need to check our voltages and make sure that that they are correct. I still don't think this receiver is performing at its top rate, because this thing should be capable of way better sensitivity than we were seeing. So you always start with your power supplies first. You have garbage power, really kind of everything else falls apart from there. So we're going to check that. It's a simple power supply. It's a split rail, so you got positive and negative voltage. And you can see the center tap of the transformer is grounded. We go into a full bridge rectifier, and you go across here. You go into this little 4195 voltage regulator IC, and there's a balance pot. And the balance pot is kind of interesting how it works. The first thing I want to say is this is kind of a strange little chip. If you look it up, it's supposed to be a positive and negative 15 volt regulator. However, even though the number here is for a 15 volt regulator, this is actually a plus and minus 12 volt regulator. Another interesting thing about this is there's one pot, and what it will do is it will raise the one side while it lowers the other, and the idea is to adjust this pot until these voltages are equal. In other words, if I make the positive 12 volts go higher, okay, go above 12 volts, then the negative 12 volts will go below negative 12 volts. if that makes sense. So that's pretty much how this works. So we want to adjust this to balance these as close to the same as we can, and hopefully they'll both be 12 volts. So let's get set up and we'll do that. Okay, we are connected up to our power supply, and the purple wire and red wire, and I'm assuming the red would be the positive and the purple would be the negative, but I'm not sure. Okay, they're even calling these TPA and TPB, so we can actually touch. So there's your negative voltage, which is negative 11.8, and then you see where it says TPA right there and TPB right there. It's basically the lead of these capacitors. And we have positive 12.3, so they are not balanced. So what we want to do, and that's kind of what I thought, is there's got to be something going on with this receiver. So 11.8. So let's see. Wrong way, of course. How many times do I turn it the wrong way the first time? If any of you that watch my videos. Okay. There's 12 volts. Let's see what this side looks like. Okay, 12.2. So we're still a little bit off, but not much. So let's go just a little hair. This is really touchy. There we go. .2, 12.05. So we got to go a little more. Man, I'm telling you, there we go. 12.1, 12.2. Let's just go a tiny little bit more. Okay. 12.25, 12.12, and I don't know how critical this is, but I imagine it has to be a little bit critical. Okay, 12.19, 12.2, that's pretty good there. I think we're going to leave it right like that because it's so touchy. Probably a 10-turn pot would be beneficial in there, but we have it set and it's good. Okay, now then, let's get back to these schematics and try to make some more sense so we can actually test what's going on inside here. Okay, all the information we have here is 2 pages. We have a block diagram, which you see right here, and we have a schematic. Again, we have no alignment instructions or anything like that to work with, so it's still going to be a little bit tricky. So first thing we want to do is just kind of figure out how this thing works and then try to apply the block diagram to the actual circuits. So when we look at this block diagram, you can see they come in with the antenna, and you go into your first tuning gang right here. The dotted lines here show you that you have 3 tuning gangs on your tuning gang. You have 3 capacitor sections. So you have your first one where you come in through your antenna. After it goes through there, it goes through your RF amplifier. RF amplifier then feeds into another RF tuning gang, tank circuit here. And at the same time, it's feeding our local oscillator down here. You then take your RF and your local oscillator, and if you notice, this guy here is 455 kilohertz above the fundamental frequency. And when we run through the mixer, we take the difference of those two, and we're going to end up with 455 kilohertz, which is how our intermediate frequency works in a super heterodyne receiver. So far, this is looking like a very basic, standard super het. From there, we go into the ceramic filters. Now, this is what's actually your wide and narrow band switch. So you have a wide and a narrow switch on the front of the tuner, if you remember. And that's what this section is. From there, you go into your IF amplifier. And you're going to go through, I believe, 2 stages of IF amplification in here, each one with their associated transformer. And then from there, we're going to come out of the IF amplifier. We're going to go into our AGC detector, which is your automatic gain control. And that AGC is going to go back down here, and it's going to vary the gain on our RF amplifier, mixer, and IF amplifier. See that? So it can actually control the gain of the circuit. This is all pretty basic on a super heterodyne receiver. From there, we go into our audio detector, which is just going to be a diode. And from there, we go into our audio amplifier and then a whistle filter, which is a pretty unique thing on this amp, or on this tuner. There are other tuners with this, but usually you see this kind of thing on more like communications receivers, not really AM broadcast. So you have a whistle filter, which is going to be an adjustment, probably. Then you have your level control, which is nothing but your volume pot. And then it goes out into a 5,000 ohm termination. So this goes out to your audio amplifier, an external amplifier. So other than that, there it is. Let's take a look at the actual schematic diagram now. So next what we want to do here is try to identify all these stages. So if we look in the beginning here, we have our RF amplifier and our two RF tuning sections. If we go here, you have an input, and if you notice there's a switch here that kind of jumpers out this little pi network here. And essentially this is going to be your local distance switch. So this is for local and distant. So it's kind of adjusting your sensitivity, your front end sensitivity. You have two coils here and a capacitor in like a pi network type thing. It's not totally a pi network, but it is, kind of. And these two coils are for matching your antenna. So you have an antenna matching section, which is really cool. A lot of receivers do not have that. From there you go into your transformer, and you see this little C1C. That's actually part of your tuning gang, which is right here. You see your tuning gang, your three sections. Okay, so that's one of the sections. And then the associated trimmer for fine tuning it, which is these little screws up here. You can see them. And then from there, we go into what looks to be our RF amplifier, which is a JFET. From our JFET, we also have another RF section, and if you recall, that's this right here. So we're here, here, and here. Okay, so here, here, and here. So that's all this. From there you go into another tuning coil, and this goes into what is going to be your mixer section. Now, the mixer also receives a signal from the local oscillator. So if we look down here, this is our local oscillator down here, and if you look, C1A, C1B, C1C, this is the next section. So you have those three sections on your tuning gang, and that's right there. And this is the associated trimmer with that. So once our local oscillator and our RF section get mixed together with this mixer JFET, it comes out, and you see they even tell you 455 kilohertz. So this is the beginning of your intermediate frequency. Now, from the IF section, we're going to feed into our ceramic filters. And you can see, here's your ceramic filters. You have this dual switch, and these switches are actually connected together. So they're those two push buttons. You push one side, it pushes them both this way. You push the other one, it toggles them both this way. And you see your two ceramic filters, and that would be right down here, these little Murata ceramic filters. And the switches, the gang switches, are down in here, these push button switches. After you choose your wide or narrow bandwidth, it then goes into your first IF amplifier, which consists of these two JFETs. And then you go through your transformer, and then you come out of that and go into your second IF amplifier, which is these two JFETs, and your second transformer. And then from there, we go into our audio detector. And right here, this little, they're actually, looks like they're using a Schottky diode instead of a typical germanium diode. Once you get to this side of this diode, there is no longer RF. It is now AF, or audio frequency. So this whole section over here deals with audio. And when we look at our audio section, this is where I'm a little bit fuzzy on how it works. But you have 3 op amps. Obviously, these are audio amplifier ICs. But you have these 3 pots here. One here, one here, and one here. I believe this one down here is going to be that whistle filter. Because you can see it's bringing these capacitors either further in or further out of the circuit, depending. So I'm kind of thinking this would be your whistle filter. And then these two may have something to do with gain or shaping of the AF. I'm not really sure. But we'll have to see what they do. Again, without really studying this. And then when you get down here, here's that AGC circuit down here, and you see you have a meter driver circuit. So there's your meter, and your meter adjustment would be this 100K pot. And then in here, this is all your AGC, and you can see how it feeds back over here and goes up into those sections just like they showed on the block diagram right there. So we have kind of an idea now of how this thing's supposed to work. So obviously, the first thing we want to do is we want to go and probably come right into here and inject a 455 kilohertz signal into here and just kind of see if these are peaked out, and kind of measure. And we can actually measure right here. We can look at our audio and just measure the amplitude of the audio as we peak out our 455 kilohertz slugs. Now, and if you notice there's 2 arrows, that means that these are dual slugs. So there's an upper and lower in there, I would imagine, which is going to be these. And I did number them how I think they're listed in there. This is number 2, number 3, 5, and 4. And then these are the 2 IFs down here, which is number 6 and 7. So these will be your IF transformers, and these will be your RF and mixer, local oscillator. So there you go. We're going to try to connect up to this now and just kind of see what we can get from it and see if maybe this can be peaked in a little bit better. Okay, as we can see, we have the oscilloscope probe connected to the audio output. So this is the input of the volume pot. So this is going to be our audio. And we're just going to look at our audio right there with the scope. And we're going to take our RF signal generator with our little injector probe. And you've seen this on other videos of mine. And I'm just going to inject the signal right here where this coax cable comes in. So you can see that coax there represents this coax right here. So we're going to inject the signal right before this input coupling capacitor. And then we're going to see if we can get these to peak out, or if they're already peaked, which they probably are. So first thing I'm going to do is go here, and then I'm going to adjust the upper coil. See, there's an upper coil here. Then if I push through, there's a lower coil down here. Okay, same thing here. There's an upper coil here, and then if I go down further, there's a lower coil down inside. So we got 4 adjustments that we're going to make on those 2 transformers while I'm holding the probe on the input. Now what I'm going to do for you is I'm going to, as I do that process, I'll put you up on the scope and you can watch if we get anything. So there we go. Zoom it in a little bit. And whenever you do any kind of adjustment like this, you want to make sure that you use as little of a signal as possible, because you don't want the AGC to come in there and fight your adjustments. So you want to make this signal look staticky. So it won't be a nice clean sine wave. It'll be a sine wave with static on it. I'm actually driving -70 dBm into here, so it's very, very low signal, relative to being at this part of the game. So I'm going to move away from the microphone and the camera, and I'm going to place the probe on there. You'll see when I put the injection probe on there, and then I'll go ahead and adjust the 4 adjusters. And you'll see on the scope, hopefully it's already peaked, but if not, we'll see what we get. All right. Okay, so the signal is on there now, and you can see how noisy it is. I'm going to go to that first IF can, and I'm going to adjust the lower, and then I'm going to adjust the upper slug. Okay, here's the lower. All right, got a wee little bit out of that. Now let's do the upper slug. And the upper one was pretty much spot on. Okay, now we're going to go to the second transformer. Oh, we got some there. And then we'll do the top one. Very little there. Okay, that's it. And all we're doing is we're adjusting for maximum amplitude. So that takes care of the IF section. We now have the signal generator connected directly into the antenna input jack right here, the 50 ohm jack. And we're still connected to the same place with our oscilloscope, the audio output. And we're now setting this for an RF signal instead of an IF signal. So I'm set at 900 kilohertz right now. And what we're going to do is we're going to tune the radio dial onto 900 kilohertz. And then we're going to, again, make a nice staticky signal that we can see. And then we're going to align the front portions of this. So we're going to align the RF amplifiers and the local oscillator. So that's what we're going to do next. So they're little transformers. You could see them right here. They look just like the IF ones, and we're doing the same thing. We're just going to go in and adjust them. So let me get back up on the oscilloscope and show you, and we'll see if we can get anything more out of these. Now, I don't know. We got something out of the IF, so let's see if we can get something out of the RF section. Okay, we're now at -80 dBm, -80 dBm. I'm tuned onto the station, at least as close as I can be. You can see right there. And I'm going to go ahead and adjust those stages now. So here goes the first one. And that one we got a little bit out of. Let's go to the next one. And these are both single slugs, these RF cans. And you can see that one actually went up a little bit. Right about there. We'll go to our next one. Alright. And we'll do our last one. And that's your oscillator there. Okay. So now what I'm going to do is I'm just going to go through this one more time and make sure it's working and that it's good, and then we'll be back. Okay, we're now at the limitations of my oscilloscope with the 10x probe and all those sorts of things and the trigger, but you see a very well-defined sine wave here with a lot of static riding on it, but I am now at negative 90 dBm, and that's with the covers off, and I did not adjust the antenna tuning coils in the front. That's more like where I would expect this tuner to work. And I would argue that probably this will do, when everything's all peaked out and everything with the correct antenna, it'll probably be able to receive, the sensitivity will be somewhere around negative 100 to negative 105, 110 dBm, which is really where you want to be. I mean, now you're approaching that of a communications receiver rather than just plain old AM broadcast. So this is how this thing was supposed to work. I kind of thought that a few of the things were out. So to recap what we did, the power supply was not balanced. So your plus and minus 12 volts was more like minus 11.8 and plus 12.3 or something like that, 12.4. I'd have to go back and look. We balanced that out. Then we went and we found that the IF section was a little bit out of peak. And we also found that the RF section was just a tiny little bit out of peak, not much. So now I think we're in good shape and we can go ahead and try this thing out once again and see how it works. Okay, we have our handy little Radio Shack amplifier on here, and you can hear that at negative 80 dBm it's copyable. Let's go to negative 90. More staticky, but we could hear it. Let's go to negative 100. And there you go. So even at a negative 100 dBm without the antenna and all that sort of thing being set up, we're actually receiving. That's what I would expect on this tuner. Now the next thing we want to look at is the audio, and I'm not sure, again, this is where we're getting a little bit of where we're going to have to look at some of this. This is where we're looking at these pots right here, 1, 2, and 3. I'm not sure what these are all about. I believe this one is the whistle filter. I don't notice any whistle right now, but I'm going to just do a little bit of experimenting and kind of get an idea of what these are doing. And if they do anything that that we can recognize and that's, you know, that I can make some sense of, I'll come back on and I'll share that with you. Okay, the first thing we're going to figure out here is getting our S meter to work. Now, on frequencies under 30 megahertz, typically it is agreed upon that a negative 73 dBm signal should give you a value of S9 on your S meter. And this has an S value meter, so I'm assuming that's what they're talking about. So I have a negative 73 dBm signal being applied to the receiver, and I have the receiver tuned to the appropriate frequency. We're going to now go down and look at the adjustment. So the first thing we want to see is this little pot right here, I believe, is what's going to adjust that, because if you look, here's this black and yellow wire, and it goes straight over here to the back of the meter. So I think it's safe to say that that's going to be our S meter adjustment. Now, it might be on, I don't know. I just set it, and I didn't really look down here at the meter because it's kind of facing funny, but let's get you on there, and you can see I'm looking through the camera viewfinder. We're a little bit under S9. So let's adjust that pot and see if that moves it. Oh yeah. Yes, it does. So let me see if I can get that aligned. Well, the pot's real dirty. That's one problem. So let's move it a little bit. And That look like S9 to you guys? That looks like it to me. Okay, so we figured the one pot out. We know what that one is. So now let me dig a little deeper. Okay, so this pot right here, this 10K, is actually your gain limit. So where you set that pot will determine what the maximum amplitude of the output of this will be when you turn this pot up all the way. So that's what that is. So this affects this. The whistle filter is this little blue pot down here, and again, there must be a procedure for it, but since I don't know what it is, I'm going to leave it where it was. And last but not least, we have this pot down here, and again, this very slightly adjusts the gain, but what it may possibly do is be more of a frequency limit pot. So what we'll do is we'll try injecting a couple different signals. We have the 1K signal in there now. Maybe I'll go to a 400 hertz signal, see if it has any greater effect than when it's at a 1 kilohertz signal. And then if that's the case, I'll come back and let you know, and if not, I'll let you know that. So we'll be right back. Okay, I'm not sure what to call this pot, but what it seems to do is it seems to affect your AF detector symmetry. So if I turn this, what'll happen is it'll kind of distort the sine wave a little bit, or it'll make the sine wave clearer. And it doesn't seem to matter if we're at 400 hertz or 1 kilohertz. The amplitude generally stays the same. All it does is it just tends to distort or misshape the sine wave. So I'll go to the scope and I'll kind of show you the effect. Okay, so we're on there. I'm at a 400 hertz tone right now. And let me just adjust it, and I'll show you what it does. So if I move it, take a look at the bottom of the sine wave. You see how it distorts, kind of clips? So this kind of adjusts your symmetry of your detector circuit. And what it's doing is it's kind of changing the bias voltage on there a little bit. That's connected directly to the, I believe, the negative 12 volt power supply. So that makes sense. So there you go. That's what everything is, and this receiver is peaked out pretty much as good as we can get it without without actually having a service manual. Again, the techniques that I used are just very simple and basic, how you would normally tweak up a normal AM receiver. So that's it, AM radio. Okay, let's get this put together and connect an antenna again. Okay, I think we're now going to get a good example of why this dial scale is spread apart so wide, because wait till you see how many stations we can tune in now with this thing peaked out.
Bill Michaels, Washington.
More than 15
Camp Fire, as it's called, wiped out an entire town, the town of Paradise, and killed 86 people. The scores...
Las Vegas Motor Speedway with Kevin Harvick on the pole. C'est important, Monsieur Jamais, et avant même qu'on fasse.
Let storms bring. Sophia says the implant would cost about
Cool sports. Every other Saturday at 10.
This is the Ohio ESPN 970 WFUN.
So as you see, every hair we got another station. And again, I did not adjust the tuning coils to my antenna. I have a definitely way non-50 ohm matched antenna right now. But again, if we tweak that in the back, it would even get more sensitive. That's how this tuner was supposed to work according to all of my understanding of it and so forth. So I guess the next thing to do is to get those amplified antennas, the DA7 and the DA9 up here, and see if we can get them working. There shouldn't be too hard to get them going. Now, to really test those out, since I'm down in the basement here on the bottom of a hill, I'm going to have to take it upstairs or something to try it out, because it's really not a fair test to use those down here. But we can definitely go through and test it and repair anything that it needs before that. So let's do that next, and I'll be right back. Okay, so we got two of these antenna things here. We have a DA7 and also the DA9, and the main difference is the DA7 is kind of like dual band. It has a medium wave and long wave, whereas the DA9 just has the medium wave, which is standard broadcast AM. Now, they both have problems. The DA9 will actually tune some stations in, but the sensitivity does absolutely nothing. Now, if you listen to this one, I don't know if you can hear it, but if I turn this down, it gets quiet. Turn it up, it increases. So at least the sensitivity knob works on this one. On the DA9, the sensitivity knob has no effect whatsoever. However, this one will not tune at all. So they both have problems. So we're going to start with this one to see if we can get it to tune. And the first thing we're going to need to do is get it apart so we can see what's going on inside. Alright, flipping this thing over, we got a neat little surprise. As you can see, somebody had taped the little, I guess it's some sort of an advertisement in there, clipping out of a newspaper or something. So that's pretty cool. So if you want to pause your camera and kind of read it, feel free. And in the meantime, let's take this cover off. I have the screws out already. And you can see there is not much going on in one of these. So we have our little power supply here, little power supply board. And unfortunately, I have the schematic for the DA9, but I do not have any documentation for the DA7, although I believe they're probably very, very similar in design. I don't think there's going to be a whole lot of difference. So let me get in here and do some tests and see what's going on and see if it's something simple that we can fix pretty quickly here. Okay, the first thing that I notice here on the DA9 schematic is that we have 1, 2, 3 elements here. So you have these two JFETs right here, and then you have this dual gate MOSFET right here. However, when we look at the DA7, let me zoom you in, you can pretty clearly see that all we have is we have the single JFET stage instead of 2 stages of amplification, and then your dual gate MOSFET down here. So this actually has a little bit less amplification on it. Again, this also has the different antenna, but again, that's just plugs in down here in this little connector right here, which is mounted up here. It's just kind of similar to a BNC type connector, but it's like a socket, just a press fit thing. And then if we go around this way, very simple power supply. You just have a full wave rectifier, two of these, plus your center tap goes to ground. They filter it with a 220 microfarad capacitor. Then it goes through a 15 volt linear voltage regulator, and then a 100 microfarad capacitor on the output of this. So that's all there is to the power supply. Nothing at all, really. Very simple. And then on the front, you just have your tuning gang, which is what you use to tune the antenna coil itself to the different frequencies. And then you have your sensitivity pot right here, which goes right onto this board. And you can see the sensitivity here on this schematic that goes up into this JFET. So I'm thinking this stage right here is missing. They're not using it on the DA7. So that's the main difference. So if you recall, our sensitivity was working, but we weren't getting any kind of tuning on this end, so we're going to have to try to figure out why that is, why we're not getting any kind of signal. So let me dig a little deeper again, and we'll keep looking. Okay, so what I'm finding is that the circuit here is a good bit different than the DA9. So the actual sensitivity adjustment is done at this dual gate MOSFET input rather than the first gain stage. So that's kind of different. So what I'm doing right now is I'm injecting a negative minus 50 dBm signal, 900 kilohertz, right into this second stage, which is this dual gate MOSFET. And up here you can see I have my spectrum analyzer connected. And by the way, I did check the 15 volt supply. It's perfect. There's nothing wrong with that. And when I inject a signal in there, you can see up here on the spectrum analyzer, can you see that? You can kind of see that I do have a signal. And if I disconnect the probe from the signal generator, you see it kind of goes away. If I hook it back up, it comes right back. Now, when I move it up to the input of the other transistor, or the JFET, and actually I'm just going to put it right on the input where the antenna is. So theoretically, and again I'm not sure about this, but if I hook that up, you can see we still have our signal there. And where I'm connected right now, you can kind of see right there, you can see I'm hooked right here where the bar antenna plugs in. And I have the bar antenna connected back here. You can see it. Kind of precarious, everything here. But what should happen is we now have an LC circuit between this ferrite rod antenna, which is what I think is in here, or a coil that's in here, and the actual tuning gang back here that I'm touching. See it? And therefore, when this circuit is in resonance, this should increase, and when I'm off of resonance, it should decrease. So if I go up here with the spectrum analyzer and I adjust that coil, or the tuning cap, it has no effect whatsoever. So we're not getting any kind of tuning action whatsoever. Now, it looks as if I'm able to pass a signal through that JFET. So right now I'm not inclined to say that this little JFET here is bad, but what I am inclined to say is that something inside the antenna is bad, and that's what we're going to check. So we're going to have to take that bar antenna apart. Now that there is a big old piece of ferrite. That is the biggest piece of ferrite I have ever seen in an antenna. Look at that thing. It's huge. So essentially all you do is there's two screws on this side, two screws on this side. These little end caps come out. And once these end caps come out, you have this with these little rabbet joints on the side, and it just slides right inside here and just kind of pushes against these pieces of foam. So we're going to pull this foam out like this, and we're going to pull this little piece of foam out like this around the camera again. There we go. And look what I see. Do you see it? So our wire's broken off. No wonder it doesn't work. So let me get that fixed, and maybe that's all that was wrong with this antenna. Okay, the brain surgery is done. So we're going to put the covers back on and connect this back together, and we should be good to go. Okay, as you can see, I have the I just have the signal generator loosely coupled with a coil. So there's a coil of wire here, and it's kind of going around the stick antenna this way, and it's just going up. I have negative 60 dBm in there right now. And now watch what happens as we adjust onto frequency. So I'm right now at about 1600 kilohertz on the dial for this antenna, and watch as I get closer to that 900 kilohertz. See how we're just slowly rising up as I turn it? And as we get closer, we can see it climbs way up. And there we are. Now, I didn't even look at this. Let's take a look where we're at. And as you can see, right on 900. What do you know? So I guess we got this one fixed. So now that this is working, let's put it all back together. Let's get the AM5 back out and let's see if it works.
Companies are actually starting to listen because
Not going to get anything down here. Okay, for a second here, just listen to the static and listen to, as I tune through the resonant point, what happens with the static. You hear that? And that gives you an idea of how this antenna and everything works. There's just so much noise down here on the bench and in the basement and everything that it's swamping out the actual stations. So really we would have to take this upstairs to really hook it up and give it a good test. And quite frankly, I'm too lazy to do all that, to move the camera and everything. But it is working now. It's working perfectly. So I will give it a test before I turn this back over to the owner to make sure everything's perfect upstairs, but probably won't put that on video just because of the hassle. I don't have a lot of time. Okay, let's we got one down. Let's get the DA9 out and see what we can find with it. Okay, I was just getting ready to start testing the DA9. I got it all apart. By the way, I did take the antenna apart and it was good. It's a much simpler antenna. It only has one single coil around the ferrite rod and two wires, so very simple. Took this thing apart, and first thing I noticed was getting ready to looks like that's going to fall off. I'm sure that has a lot to do with the problem with the lack of sensitivity on this thing, so we're going to tighten that up for starters. And it looks like this thing has had some force on it, because if you kind of hold it at the right angle, you can see down in there how this aluminum top is kind of distorted a little bit. So it probably just got loosened up from banging around or something, but we're gonna check that out, and then we're going to still go through and inject a signal in there and kind of see what it does. Okay, I'm going to try to do this around the camera. So the first thing we want to check is the front ends here. So we're going to inject the signal here, and I'm using that little probe that I use a lot on a lot of my videos from a signal generator. Again, we're at 900 kilohertz, and we're going to see what kind of output we get. Then we're going to move it back here, and we're going to check and see what the output looks like. So we're going to kind of follow it down. So for instance, and if we go to just to the output itself, just to give you an idea, watch the screen. There's your output. Now if we go back to these two gain stages, so we'll go to the first one. We'll go back to, this is Q2. Touch the gate and see, notice how the amplitude is higher. It's actually amplifying it. So you're at negative 50 dBm there. And I have a negative 60 dBm signal. So you can see it has amplified the signal. And then we're going to go back even one more to the very first JFET. Touch that. And if you notice, there's negative 40. Actually a little more than negative 40, negative 39.1. So this thing's working perfectly. So now what we want to do is just kind of see if the tuning part of it works. And in order to do that, we have to hook the antenna up and then put something in the front end there. Inject your signal in the front right here and see if we can tune through it and if it goes in and out of resonance. Okay, we got everything hooked up, and I have my outside antenna, which is a 43-foot vertical amateur radio shortwave antenna. And I also have this, and basically when this is turned off, we're running off of the outside antenna, which is really unfair because it's outside and it's more out in the open. This thing's down in the basement, so you can imagine with all this junk on my bench. But I just want to give you an idea of how well this works. This is a pretty clear station that I have tuned in. Unfortunately, it has music on it. We can't turn it up for very long, but I'll just give you an idea of switching between this antenna and a really good outdoor antenna, how well this works.
Still shut down a party. I can hang with anybody. I can drink whiskey.
Okay, that's all I dare, and I'm wondering if I'll even get flagged on that little bit. I'll tell you, the YouTube algorithm has gotten really bad in the last month or so that I've noticed. When I go to upload a video, I mean literally the tiniest little snippet of a song, it comes up and tells you there's something on there. You don't really get a copyright flag on it as long as you're not posting it yet, but it gives you the warning and you have to delete it or demonetize it or whatever. It's a pain. The only thing they got left to do now is to copyright the static. I guess they'll find a way to do that too. I shouldn't complain. This is a free service that YouTube provides for us, but it is kind of annoying that you just want to play a sound for somebody to hear. But anyway, that gives you an idea. You heard the static come through on the external antenna or on the DA9. That's to be expected being where it is down here, but notice how well it worked. The other thing I'm going to show you is when you turn this on, pay attention to the meter. You can see it down here in the corner. Let me just move this down just a little bit and over just a little bit, and watch when I kind of tune off of the frequency. Watch what happens to the meter. See how it drops down? So like when you can actually see how it peaks out and as you go through it. So it actually works really well. So there's a little demonstration. By the way, the sound quality going through an actual amplifier, as you could tell, is really, really good quality. When you have a clear AM station, this thing, you can't tell it from an FM radio. It just sounds crystal clear. So let me get this cleared off, and I want to show you a couple more things about this that I found out. All right, let's talk a little bit about what this whistle filter is. As you may or may not know, depending how much you're into radio, the way that AM broadcast is arranged is that the channels are separated about 10 kilohertz apart from one another. So what that means is every 10 kilohertz on your dial scale, you can have another AM radio station if there's one in the area. Now, that presents a certain limitation to us, and that is that you don't want the amplitude or the modulation of your carrier wave. The carrier wave is the actual radio station, and the modulation is the audio that's riding on that. If that audio signal increases in frequency up to 10 kilohertz, it then will create a secondary tone. That tone will actually what's called beat against the adjacent channel, creating what's called a beat frequency. If there is another station that's nearby that's on that particular 10 kilohertz higher or lower station, what's going to happen is those two frequencies are going to kind of beat against one another, and you're going to get this whistly sound, this whining sound. So one of the physical limitations of AM radio is you can never have a frequency that's 10 kilohertz or higher. So, or you'll be spilling over into the next radio station area. So that's one of the reasons, that's why you see AM radio only topping out at about 8 or 9 kilohertz. That's the physical limit where they set it, where any frequencies above that are going to be kind of filtered out at the broadcast end of it. But what happens if we do get a 10 kilohertz signal in the station? Well, you're going to get those terrible chirping, whistling sounds. So what they've done in this receiver, and in many receivers, is they put what's called a notch filter. A notch filter is a filter that will only filter out a certain narrow range of frequencies. This one in particular is set to filter out 10 kilohertz so that you don't get those whistles. Now, that's what this pot is for adjusting, and I'm going to demonstrate to you how it works. So give me a second. This is the pot right here we're going to adjust. We're just going to move it up and down, but I'll show you what it does. Let me get you back on the oscilloscope. Okay, what you're seeing is partially about a 2 kilohertz sine wave. That's 2 kilohertz audio signal. And you can see how strong it is, how high amplitude that is. It's going clear off the scope, off of the screen. It's such a high amplitude. So that's a nice strong carrier now, or audio. Now what I've done is I've just put an audio generator. I've connected my audio generator. Well, I guess I'll show you because everybody will ask. Right there, it's just a simple audio generator. That's all it does, is creates audio frequencies from, it'll go from 0 hertz up to about 1 megahertz actually. And I connected it on the external modulation input of my signal generator. So I'm just modulating that 900 kilohertz station with that signal generator. So if we go back over to here, and I'll lock it back down, go back over here, what I'm going to do is I'm just going to adjust that knob on that audio generator, and I'm going to increase that frequency. So watch what we do. And notice as the frequency increases, there's 4 kilohertz, there's 5 kilohertz, 6 kilohertz, and notice now that the amplitude is starting to drop. 7 kilohertz, 8 kilohertz, you saw a real drop off now, right? Here's 9 kilohertz. Now watch what happens when we get to 10 kilohertz. At 10 kilohertz, it almost extinguishes that signal. You see how it's way squished down. Now watch what happens. I'm going to adjust that pot that I showed you in there, and watch what happens. See there? And as I sweep through that peak, I get this thing tuned in properly, it will suppress that 1 kilohertz, or that 10 kilohertz tone. That's what that does. Now watch what happens when I go a little bit above 10 kilohertz. Now that I'm above 10 kilohertz, it pops back up again. So it's really a narrow filter, and it's designed to suppress anything that's going to interfere with the next adjacent channel. Okay, and if I went down in frequency or up in frequency, it doesn't matter. It's going to cut out anything that's 10 kilohertz of an audio signal. That's it. So that's what that does. That's how that whistle filter works. Now, one last interesting thing about this is these little notes here. You can barely see them. There's a black wire, red wire, and a gray wire. There's 3 wires in there. And what that's for is there's a company called Medici, I think it's pronounced, that makes a adapter that you can put on this that will adapt this for that Sequam AM stereo. So this could actually be modified to tune in AM stereo with an external modification. And this is the 3 places you wire it up. Maybe someday, if we ever get into that a little more. I don't have an AM stereo signal generator. It would be nice to have one, but they're not that easy to come by all the time. That would be another neat experiment to do. So now the other thing I want to go over is I did get some of the specs on this thing, and I kind of want to review them with you. And if you can recall back to when we did our initial test on this, you'll notice that this matches very similar to what our test results were. And actually, I got this information about this after we did those tests. So it was very interesting that when I read this, it actually matches what we measured on our oscilloscope and on our spectrum analyzer. So let me show you that here in a minute. Okay, so taking a look at this, for 10 dB signal to noise ratio, now we of course did SYNAD, which is 12 dB for SYNAD, is what we were looking at, but the sensitivity on this was 3 microvolts. And if you convert that across a 50 ohm load, that actually will translate to about negative or minus 97 dBm. And if you recall, it was right around that minus 96, minus 98 dBm, just around minus 100, that this was still picking up a good 12 dBm or 12 dB SYNAD signal. So this tuner actually performs, 30, 40 years later, just like this. And this is from Audio Magazine, August of 1976 article. So, and then they show you the actual frequency response here on it with minus 3 dB down, 3 dB down points, 15 hertz. And if you remember, we measured it at 20, and it was rock solid at 20 hertz, and to 9 kilohertz, and that's realistically, and it was about 3 dB down at 9 kilohertz. When we looked at 30% modulation, which is where we were setting our tone, with a 1 kilohertz tone, it's about 0.5%, about a 0.5% THD, and we were testing it at 400 hertz, which was a little bit higher, but not bad. So again, it was matching all of this. So that was really interesting. I was really surprised that really without doing a whole lot to this thing, other than a little tune-up, how well this thing performs. So this is going to be a lot of fun for the owner. I'm sure he's going to enjoy it for many years to come. And again, I really like the DA9 and the DA7. That's a nice combination with this. And so that's about it for this whole video. I hope you enjoyed it. I really enjoyed it. It was quite an adventure. I can't wait to see how this thing edits out, because of all the things that happened throughout the course of me making this video and working on this. So without any further ado, I want to wish you all peace, joy, happiness, and good health in your lives. And until next time, stay well. Bye-bye.